everyone, welcome back. Next up, we've got the question that's been on all of our minds. What do you get when you combine a snake and a squirrel? We're going to have Caito Scherr talking about how to build a Python data pipeline with Apache Flink. Caito's a developer advocate for Vivarica, the creators of Apache Flink, representing the US region, and is based in Portland, Oregon. Previously, she was a software engineer at a data analytics company and loves geeking out about metrics and stream processing. Outside of tech, Caito does woodworking and construction, dance, running, and appreciates terrible puns.
Great. Perfect. All right. I'm going to go ahead and get started. Can everyone see my slides all right? Cool. All right. Welcome, everyone. And welcome to What Do You Get When You Combine a Snake and a Squirrel? And this is going to be about building a Python pipeline using Apache Flink's PyFlink. As you mentioned, my name is Caito Scherr, and I'm the developer advocate for the US region at Vivarica, which is a Berlin-based tech company that's home to Apache Flink. I live here in Portland, Oregon. Hey, West Coast, it's really good to see you. And side note that's related, just got power back after about 5 days without it. So there's a few things that didn't quite make it into the talk. So I'm going to try to put a blog post out afterwards to make sure I got everything. So feel free to check for that later. I'll have a link at the end. But more importantly, a shout out to everyone else who's dealing with that this week, regardless of where you're from. I really hope all of you were able to keep safe out there. And thank you so much for still making it here. We are so glad to see you, though. It really means a lot. And as for what I'm going to talk about today, so why combine a snake and a squirrel in the first place? And what does that even mean? So any symbiotic relationship among very different creatures has unique challenges, but can result in something even more powerful than the sum of its parts. Combining Python with Apache Flink, which of course has this adorable squirrel logo, has its complications, but it can also produce something incredibly fast, portable, scalable, and highly flexible in your application, particularly for data pipelines. And getting started with stream processing for Python can be hard enough. And the more complex the streaming framework, the more intimidating it can be. However, with this particular combo called PyFlink, each area of complexity there brings with it this level of flexibility and robustness, which can result in this awesome fusion that can be leveraged to really improve and accelerate a pretty large number of Python use cases. So that's what I want to talk about today and what this combination looks like, why and where it's advantageous, and some best practices for getting started. I'll start with the most relevant, which is how does this affect you? I mean, really, that's kind of the most important thing here. And what problems is PyFlink intended to solve? And once you're actually invested in this problem space, then I'll go into what PyFlink is and how it works. And lastly, I'll go through some examples of how PyFlink does address these issues and using some example pipelines and getting a look at kind of what those look like architecturally and in a code demo. Okay, so the fun part, how does this affect you? So let's say you're a Python engineer, probably very likely at this conference, and you're working on a project that needs to be able to scale up and down rapidly and needs to be reliably distributed. Maybe you're doing something like anomaly detection and you need your data to be very precise and accurate and accessible in near real time as possible. Or maybe you're doing machine learning or another situation where you can just access your data whenever, no problem, but you're dealing with these mass amounts of data or doing really complex transforms and modifications that otherwise might have some really high overhead on performance. And if you had to wait for all of that data to go through your pipeline in these start and stop batches, or even just using like a simpler stream processing engine, that might be kind of a pain. So that's really kind of the core of what we want to go into with this. So what is PyFlink? So we know now that it's Python combined with Flink, and that its purpose is to allow users to leverage Flink's features for Python use cases. And that's great. But if you don't know what Flink is, that's really not going to be helpful at all. So I'm briefly going to cover some of what Flink is. And if you're already familiar with it, feel free to tune out for the next 2.5 slides. I'm counting this slide as half for some reason. So the rough translation of the word Flink in German means nimble. So it's really highlighting that flexibility and the speed of this framework. So that's something I want to keep in mind here. And Flink does now have unified and batch streaming capabilities, but it's really still foremost known as being the stateful stream processing engine. And it's particularly flexible and, very complex framework. and it was built to address a lot of the common challenges that come with stream processing. Namely, this is being able to provide features like high availability, extremely high throughput, various other safeguards for your data system, and exactly once guarantees. As in, if there's an interruption or killed process, etc., data that's being read in after that restart is not going to get lost or duplicated. That's actually my absolute favorite feature. I love geeking out about it. Partially because with Flink, it scales really well. So that's something that can be pretty hard to implement. And I really appreciate how it works in this technology. So all of these challenges, while maintaining high performance, low latency, and as I mentioned, scalability for each of these. It's also highly customizable, so it can be used for a wide variety of pretty specialized use cases. And the most common cases, though, are data pipelines, particularly for fraud and anomaly detection, where data needs to be extremely precise and accessible in as near real time as possible, and often requires a lot of complex transformations, and for that to all happen pretty quickly. So Flink also includes various additional options and APIs. We covered it being the stateful stream processing engine. So that's this low-level one that we have at the bottom here. And then on top of this, we have Flink's core APIs. The really relevant one here is the data stream API. And then we have our table API, which is also going to be very handy later. And now also this high-level SQL functionality, which in particular has really shined and had a pretty impressive amount of development velocity this past year. Pretty cool new features that do relate pretty well to PyFlink, but that's a whole other talk. So won't actually be getting into that as much in this case. So a quick note before I go into the architecture. I'm assuming that most people here are at least somewhat familiar with stream processing. So due to time, I didn't include that. But that assumption may not be accurate at all. So if you want more info on streaming or streaming with Flink or any of that, I have some resources that I put together that I've linked at the end, but feel free to also ask me any of these questions, and I will leave my contact info up at the end as well. I love geeking out about this, so happy to answer any questions. So again, this is a typical Flink application, at least specifically for a really basic data pipeline. And I was going to say on the left, but because of mirroring, this may not be your left. So I'm just going to say this box here, which we have our event producers. Again, pretty straightforward. This is any of your sources. So it could be applications, sensor readings, etc. A lot of options for what that can be, especially because it's typically just going to be put into another data stream or a message queue, like a Kafka topic is really the most common, before it's ingested into the actual application. This could be one stream, multiple streams, etc. And then the application itself on a high level consists of the app's application business logic, as well as the locally stored state. And it ingests the streams and filters, modifies them as necessary. Again, very straightforward. Modifications often include maps, reduces, complex data transforms. And Flink also provides transformation categories for things like Lambda functions, such as, among others, keyed stream, where events, it's applied to events with respect to a particular key, multi-stream. It could also merge streams into a single stream or split one stream into multiples. I'm mostly just saying this to make a Ghostbusters joke because, yes, you can cross the streams here. It's a good thing. It can still be complicated, but it can be very powerful. And as you can see, this application is also paired with local storage that enables the current application state to be stored regularly. And this is not quite the same as like a snapshotting system, but it's similar enough kind of for this basic description. So this is where the stateful in stateful stream processing comes in. And not all stream processing frameworks are stateful, but Flink is, and it's a very core component of this technology. So I really wanted to make sure and highlight that. And then after this, again, going back to the really straightforward stuff, data can be written to a variety of sinks, databases, local external storage, even other streams or other streaming applications. Okay, so then is PyFlink just sort of this like mashup of the two? How does that work? And there's really a lot of very nuanced under the hood work and decisions that went into this combination that, again, for the sake of time, aren't really particularly worth going into here. But if you're interested, that's also going to be part of the resources I'll link to at the end. But the most important part, and at this really most basic level, is that PyFlink is a Python API for Apache Flink, intended to allow you to build scalable batch and streaming workloads. And it was created as a way to benefit both the Python community and the Flink community through enabling users to really leverage as many features from both as possible, ideally everything. And on that high level, and of course for the Python side of things, because that's our focus, this means the priorities here were to make Flink's table API and the DataStream API seamlessly available for Python users, as well as UDF support and integration with Pandas and other Python libraries. So those two APIs that I mentioned, table API, which allows for powerful relational queries. So this is similar to using SQL or working with tabular data in Python. And then there's the PyFlink DataStream API, and that's the one that has that more low-level control, particularly for things like state and time. So that's going to be for your like really more complex streaming use cases. And all of this was packed into the first year and a half of PyFlink being around. And I just think this is really exciting. It's still relatively new. And a lot of these contributions came from our really awesome open source community. And so I always like to give a shout out to our open source community, especially these sort of conferences, because that's just really neat. And so as part of this, these features have been progressively more separated from each other in a way that makes it possible to do things like download PyFlink from PyPy and create UDF straight from the Java table API or SQL and really have it be a little more modular. And I'm going to go over some of the UDFs that I'm providing some basic examples for each. And I wanted to kind of as a caveat mention that some of the slides have a bit more code on them than I usually like to put on a single slide for readability. So I wanted to say that the upcoming couple slides are just really basic examples of what this generally looks like. And you don't need to know all the details in order to understand the concepts or in order to understand the upcoming demo either. So again, just very generic examples. And then there's more details on all those in the docs as well. So as I mentioned, UDF support was a really big focus in the development of PyFlink, particularly to ensure that it would actually fully support all current Python method definitions. UDF support was launched alongside dependency management just a couple releases ago, and it also included enabling full third-party Python library use, which is pretty sweet. So again, this code is just to outline that there's a lot of different options for defining a UDF in PyFlink, and mostly really just to highlight that the development of PyFlink really wants to keep up alongside with Flink's goals of just really staying flexible and highly customizable. So for the general UDF options, we have scalar, table, and aggregate functions. And additionally, there's vectorized UDF options, which includes vectorized scalar and vectorized aggregate functions. And I'm going to go over the vectorized UDFs a little bit, but again, for sake of time, the general UDFs, there's some really well laid out documentation, so and including different ways to define each function. So I'm not going to go into those as much in depth, but we will get to see some of them in action in the demo. And at the most basic level, so scalar functions in Flink work very similarly to how they'd work in regular Python. And of course, table can produce various numbers of rows as output. So again, very similar. And there's going to be a couple slight differences though. So for instance, like the return type of Python table functions in PyFlink need to be either iterable, iterator, or generator only. And the aggregate functions have some different implementation requirements depending on whether you're in streaming or batch mode. Again, all of this is in the documentation and it's otherwise very straightforward and very similar. And the biggest highlights here is the added functionality of Pandas. So I want to get into that one a little bit because that's just really exciting for me. And what's so special about this is it includes a conversion option in PyFlink between Pandas data frame and table. So additionally, the way that Pandas was integrated into PyFlink was able to significantly improve serialization and deserialization performance, so particularly for vectorized functions, and it enabled a much smoother integration with other Python libraries like NumPy. And this is particularly partially possible due to the Apache Arrow under the hood to transfer batches of rows that are going between the JVM and the PyVM in a columnar format instead of just going row by row, which of course is where you'd get that high serialization, deserialization overhead. And there's actually even configuration options to customize a cache layer that can further adjust your performance depending on your use case. So again, I just really love geeking out about how this integration worked. These batches are then converted to Pandas series, transferred to the Pandas UDF, at which point other Python libraries like NumPy can be a bit more effectively leveraged. And all this allows for better parallelization for distributed workloads. So I like this just because it's a great example of just really the whole point of leveraging the full functionality of both Python and Flink streaming capabilities. And this is the more fun example, a basic conversion from Pandas data frame to the PyFlink table. The conversion of PyFlink table to Pandas data frame is actually way shorter and simpler, so I decided to go with a more exciting one for the example here. And then as for vectorized UDFs, all vectorized scalar functions can be used. They can basically replace any of their regular non-vectorized counterparts. All of the optimization to make them vectorized, again, is done under the hood, but there's some options. Also, all of this is in the docs to configure the size of the batch that's converted to Pandas series. And that's the one that we talked about that's transferred between the JVM and the PyVM in the last slide. And essentially, these functions take Pandas series as the inputs, return Pandas series of the same length as the output. So very straightforward. And then as for the vectorized aggregate functions, they simply take one or more Pandas series as inputs and then return scalar value as output. There's a few more prerequisites for their use, though, as I mentioned, but with those prereqs, they can be used to replace various aggregation functions like group by aggregation in both batch and stream situations. Just to recap, though, the biggest benefit here is really having that higher performance and that decreased serialization, deserialization overhead. Okay, so now that we have the basic, we can get into the really fun part. So firstly, okay, basics again. Back to basics. So I don't want to take too much time just regurgitating the docs, but I did want to mention a couple basics that are nice to know ahead of time and are also often forgotten. So this is just more kind of a PSA. So I know I've forgotten to swap my Python version back a couple times, and I know I'm not the only one. So I really want to hammer that in. PyFlink does require Python 3.5 or higher. And then, as I mentioned before, you can just download it from PyPy now. So that's just really nice and simple. And additionally, you can use configs to specify the Python interpreter. There's various options for setting up your virtual Python environment for PyFlink. And in kind of keeping with that highly customizable goal, there's a ton of different configurations. So I definitely recommend checking out the docs for this, especially if you're if you feel like your use case might be particularly complicated. Okay, so with that, there's a couple different examples I could give, but I really like this one that my coworker actually made. My coworker Marta Pays, so shout out to her. And she put it together, this data pipeline, and does a really great job of highlighting a lot of what we've just covered. So she started with a real world problem we have at work. The Apache Flink open source community has an incredibly active mailing list, which is awesome. But in order to really get the most out of it, she wanted to use PyFlink to more effectively analyze and sort topics into some of the more common questions we receive and be able to get some more meaningful data out of that. So as an overview, she started with a couple of prerequisites around model training, wrote a 5-step PyFlink pipeline, and then connected it to Superset in order to visualize the output. So as for these prerequisites, first, she used Python GenSim library to train a model on, I can never pronounce this right, so we'll see how I go, latent Dirichlet allocation, or LDA algorithm. From now on, I'm only going to use the acronym. And if you're not familiar, this is a generative statistical model often used to determine why some parts of a data set are related or similar to each other. And second, this model was passed to PyFlink along with the necessary libraries, all of this, within a UDF, and mainly in order to classify the source data from Postgres. So with that pre-work done, the first step of any Flink application is typically to set up your source and sinks. And in this case, create tables for each. So this is using the Python table API. So this is one of the 2 APIs that I brought up earlier, but it should still look pretty similar from some of the slides that we saw in the last section as well. So I've got a best practice alert. So it is best practice to use SQL DDL here. So this includes specifying, in this case, the connector properties. So here we're using JDBC, which is connecting to Postgres. And more specifically, there's a base table with historical data for that mailing list and a dimension table in order to look up the topic descriptions. The second step is to clean and label the messages, and this involves writing a UDF for that purpose. Now, as we saw earlier, there's many different ways of declaring a UDF in PyFlink, but the easiest way is to just add the @UDF decorator to your function with input and output data types specified. So just like she does here, again, just going with the most straightforward example. And this is also where that LDA trained model gets loaded. As an important note, she's also added a tokenizer to clean and preprocess the data. So very important, another kind of PSA best practice, very important step for getting really good, meaningful results in your data. And this is where the Pandas optimizations that we talked about earlier come in. So without that functionality, the serialization and deserialization would significantly impact performance. And again, this is a simple example, but this I cannot express to you how massive this mailing list archive is. So it's a huge amount of data. And so we really want to make sure that we are maintaining good performance. And by using the pandas as the UDF type, and again, being able to leverage that Apache arrow under the hood. And just as a recap, again, this is making sure that we're using columnar format when we transfer from JVM to PyVM, instead of that one at a time process for our rows. So subsequently, this can then be passed to the vectorized UDF in a Panda series format. So thirdly, is to build the query that calls the vectorized UDF, looking up the topic name for each message from the mailing list. I feel like that's like my shortest speaker notes for the slide that has the most going on. So I'm just going to leave that up there for another second in case you want to get another look at that. So the final step is then to actually run it. So this involves submitting a job to the PyFlink cluster. And this particular application can be started just with a Docker compose command, which you can see right up at the top there. So there's actually two images. We have the console up top, and then we have our UI at the bottom. And we have a little key on the, for me, it's the right side, notifying, so each thing that's happening in the console, letting you know which part of the process that is. And then the bottom part for Flink and for PyFlink, they all come out of the box with this nice handy UI, and it defaults to port 8081. So you can visualize all of your jobs and status just right on localhost. So right now we can actually see our job running. And I timed that just when we were able to actually see that as the GIF rotates. So that's pretty fun to be able to get to see that. And then speaking of visualizations, the very last step is then, so we have this count here, but then now we have this really nice chart that has our most common topics per month pulled out of that long threaded depths of this very large active mailing list. So nice conclusion to that. So as a full recap, so what it is, PyFlink is the Python API for Apache Flink. As for why, PyFlink was built to enable users of both Flink and Python to be able to fully leverage all features for each technology, particularly for stream processing Python use cases. This really symbiotic relationship is possible through making Flink's table API accessible to Python and using PyFlink's UDF functionality, and in particular, the Pandas integration that allows for higher performant vectorized functions. And with that, thank you so much for coming. And I just wanted to say, especially, I think I'm already running close to my end time, cutting into Q&A, but really, really huge thank you for the PyCascades team. I am so genuinely honored to have gotten to work with this amazing group this past year, and especially all of the support during this past week, during the power outages, really, truly heroic efforts there. And a major shout out as well to my coworker, Marta, for putting together this awesome program. And with that, I'm going to leave my contact info up there. So feel free to hit me up for questions about any of this over Twitter or email. And then I have a couple related blog posts and talks that I've linked to under content, so Medium and my website. And I will be posting, I would say within the next month. So yeah.
Thanks for the fantastic talk, Caito. That was really exciting and really cool as somebody who works with these kinds of data sets to see the tools that are coming out for managing them. Next up, we've got All About Podcasting by the hosts of Talk Python to Me, Test and Code at 4:20 p.m. Thank you.
Nice. Cool. Thanks so much.